Powered lower limb prostheses have helped individuals with amputation regain functionality that passive devices cannot provide by replicating normative joint kinematics and kinetics using sensors isolated to the device itself or the lower half of the body. Our work looks at expanding the sensing available to the controller by including center of mass kinematics to coordinate control at the system or task level, which may promote synergy between the user and device. We consider this methodology due to the pivotal role of the center of mass imbalance. An able-bodied walking dataset is used to generate reference center of mass kinematics and ground reaction force trajectories, which are the task-based equivalent of reference joint-level trajectories used in literature. These task-based reference parameters are used in conjunction with real-time data from an XSense motion capture suit to determine the desired output torque from the actuators of the prosthesis. A feed-forward torque is generated by translating the ground reaction force profiles to the configuration Jacobian, while a feedback torque is determined by the discrepancy between the reference center of mass position and real-time center of mass estimation. This methodology is active during the stance phase of the gait cycle when ground reaction forces would be present. This framework was tested with an able-bodied individual donning the open source ankle via a bypass adapter at their preferred walking speed. During testing, the user walked on the device when operating in passive mode, as shown on the left, and using task-based control, as shown on the right. The user walked on each controller for 60 seconds, achieving at least 40 continuous strides per controller. Statistical analysis looked at how well each controller tracked the reference vertical center of mass trajectory throughout the gait cycle, which is represented by a dashed line here. The task-based controller resulted in a statistically significant improvement in tracking the reference center of mass trajectory, particularly through the stance phase where the control method is active. Looking at the joint level response of each controller throughout the gait cycle, it is readily seen that the passive controller does not provide any plantar flexion push-off at the end of stance. However, even though there is no explicit consideration of joint level characteristics, the task-based controller achieves qualitatively very similar ankle-angle progression throughout the gait cycle to normative kinematics, illustrated by the dashed line in these plots. This includes plantar flexion push-off. These results support the idea that these joint level characteristics of walking arise from whole body coordination via center of mass considerations. Likewise, center of mass feedback helps promote synergy between the user and their device from this task level perspective. A benefit of this framework presented here is its generalizability to knee-ankle prosthetic control. As illustrated in this plot, the desired knee torque calculated throughout the gait cycle during the trials conducted in this work also shows qualitative agreement with normative knee torques. Future work is focused on extending this work to control the knee-ankle configuration of the open source leg. Thank you.